It's time for another math easy. So we're going to discuss basically evaluating integrals again, but now we're going to compare the midpoint versus right endpoint approximation and show that the midpoint one, it's usually much more accurate, but basically we use right endpoints because it's just more convenient to write it down. You can see my earlier videos, and I'm going to do this example that I showed in my earlier evaluating integrals examples part 1 video. You can see that in the video link below. Basically, so this one here to calculate the integral of x to the 3 minus 6x. So this is yeah, using the infinite rectangles. We're not in antiderivatives quite yet. Do that later. But anyway, so with this, I showed that the exact integral of this is equal to, in the video there, it's equal to, negative 6.75 here. So this is the exact answer. Yeah, and also, and if you graph it out, it looks something like this here. So then, remember that this, what this integral, all it means is you're just gonna have a summation. No, actually, a limit as n goes to infinity of a summation from well, I is to 1 up to n of f of xi times it by delta x here, and then this is basically just a summation of rectangles. So you would just make it, yeah. So it's something like this here. This is using right endpoints. So you would go down here. This is delta x. And delta x is equal to, just going to be, well, the difference here, this is going to be 3, well, minus 0, which is, this is the 0 here, x is equal to 0 divided by n. So we divide it into equal, equal widths of rectangles, and etc. You keep doing this one here, and then you're going to get a negative area here. I'm just recapping what I did before. And then you would add this positive area here of these rectangles. You're gonna have a net area here. That's what the integral is equal to. But then, so if you use right endpoints, we use right endpoints usually because it's just easier. Because if you look at this one here, if this is x1, this point, this is x2, etc. This, then you could just plug it in right away. So this is gonna be x1. So then the area is going to equal to, we'll just call it Rn here. So summation, so Rn for right endpoint. So the summation of this delta x f of xi, where, so then all these points, all these stuff, this delta x is going to equal to, well, 3 over n. That's what, this is just a difference divided by the number of rectangles. So this n rectangles, arbitrary amount. And then xi, well, this one is equal to, because initially here, this is, so we have initially x1 is equal to delta x here, and we're just shifting by a delta x, so x2 is equal to 2 delta x, etc. all the way up to, like, say if you had a random one here, this is going to be xi, this just equals to, well, I times delta x, so the number of rectangles, this is the ith rectangle. So then this xi is going to equal to I times delta x, and then f of xi is just going to be, we just plug that into the formula here. So f of xi is equal to xi cubed minus 6x. Yeah, so I've made the Excel sheet that I already, and I also showed in that earlier video, I made an Excel sheet basically calculating all this for a various amounts of n here. I went from 600 and 1,000. And now instead of doing this one, if we use midpoints, it would be much more accurate. Yeah, so now here if we use midpoints here, if we call this x1, this is going to be, let's just make it bigger so it's easier to draw. So now instead of finding what f of x1 is, we just split it in between here. So we'll call this one x1, we'll just put a line above, so meaning average. It's usually what the average is. And then, so we draw this line up here, and now this is going to be our new delta x. Oh no, delta x is always the same. I mean, it's just going to look something like this here. So we're going to use this approximation, and we split this in two. This is going to be x2 over n. Over this average sign. So then we just go up here. So now we use this point here. So then this one's going to be f of x average 2, or the midpoint. So we do this for every single one. Yeah, so here if you have xi and xi minus 1 in this case here, and then, so then if we just have an arbitrary one here, we would put this xi, let's call this xi with a thing on top average, so we would just do it arbitrarily here. Yeah, and then we would use this xi here. So instead of, we keep doing this until, we sum up every single thing here. So this is always the midpoint. Just draw, so draw midpoint here. So you'd always only go in the midpoint here. So we just draw like this, and go down, etc. So you keep doing this for everything. And then if we write down the formula, we'll just call this mn, meaning midpoint. So we're going to be this summation of delta x times it by now f of x, what's called xi center here. Actually, this is a 2 here. That was for the 2. This is for the I. So now we're just going to have this one here. So all we gotta do is just write it in terms of, write what this is in terms of delta x. So in this case, yeah, we know that this is just the average. The midpoint is just the average, so xi prime is going to be equal to, well, the average of these two, and the average is just summing up divided by 2. So we're going to have xi minus 1 plus xi divided by 2. And we know xi is just equal to, well, from above, it's just going to be equal to I times delta x. So we know all this one here. We know f of xi is just going to be, well, we're just going to write this is equal to whatever this average point was to 3 minus, this is going to be times 6. Yeah, so now that we've set up all these equations, we can, I'll just show you the Excel sheet that I made to compare these two approximations. Yeah, so here's the Excel sheet that I made basically for, we'll call this 6 rectangles here. I've set it up for, you just write down this i's up to 6 rectangles here. So sum up each different area here. So we would get xi first, which is just equal to delta x times it by whatever I was. And then the midpoint is going to be, well, this one is going to be divided by 2 because it's the initial one's 0. But as you can see, this one's going to be the average. So this, the I in this case minus the one before divided by 2. I mean plus it and divided by 2. So we get the average. So the average of 1 and 0.5 is 0.75, etc. Do this for every single one. So f of xi with using right endpoint is just going to be this. It's just going to be this to the power of 3 times minus 6, etc. Then the midpoint we just do the exact same thing, so we use this midpoint one. And the right, then the right sum for the first rectangles is going to be delta x times it by this point here. Yeah, so delta x times it by f of xi. And then the midpoint is going to be times it by the f of xi midpoint one. So that's all we do here. Then we sum it up. And then we know that the answer is 6.75 or negative 6.75. So then you would sum it up for 6 rectangles. You could see that the right endpoint is way off. It's negative 3.9. This one's negative 7. And the error of this one is negative 2.81. This is 0.28. So it's much closer. So then I did the same thing but with 100 rectangles here. Let's just see how accurate they are now. So as you can see, this one's already at negative 6.75 here. So this is much more accurate. So if you're developing a calculator or whatnot, or this might be how the calculator does it, does integrals. I'm not sure what method they would use, but they would consider what's more accurate faster, because just so be less calculations that you would have to do in your calculator. So now as you can see, this one here, 6.75, is negative 6.6, so it's still it's getting closer, but this one's already pretty close. It's 0.001 accuracy there. And then if we did, then I did this one for 1,000. So there's 1,000, the same formulas here, but now we're just using 1,000. We have 1,000 rectangles, and then if we see this, look at the accuracy of this one. This one is not even, it hasn't even got to 6.75 yet, and this one it's already there up to, let's say, 5 decimal places here, 0.001 here. So yeah, that's what. Yeah, so from this you see it's much more accurate. Yeah, so I've just summed up the values here for Rn and Mn. So you can see this one here at. Yeah, this one is much more accurate and is faster converging here, because you can see for the midpoint one at 100 rectangles you're already at 6.75, and then if you use the right endpoints, even at 1,000 rectangles you're still not at 6.75. So as you can see, this is just much more convergent, and so this would be better if you were writing a calculator on summing up integrals. Using this method would be better, but this one's just easier to write because the xi is going to be I times delta x, where this is going to be the average of whatever your two previous ones, or your previous and your initial xi is. So that's why it's just easier writing the right endpoint. But you can see the midpoint is usually the most accurate, and that's I just wanted to show that. That's hopefully learn from this. And we can download these notes as well as the Excel file in the Dropbox link below. And stay tuned for another math easy solution.